The next example is also a geometric series. We have 3 halves raised to the n, and the summation as n goes from 1 to infinity. So we have the first few terms listed out here. What we're going to do is list the first 5 sums of the first 5 partial sums of this series. So again, for s sub 1, it's just this one. S sub 2, it's the first 2 added together. S sub 3, it's the first 3, and so on. So again, you don't have to wait as I type that into the calculator, but here are our first 5 partial sums. I think you'll see right away why I only had to find the first 5 this time. We want to think about, what do we notice about the results? Well, it gets bigger each time, right? If you look at each term in this series, the term here is bigger than the term preceding it. So each time we add, get a new partial sum, the partial sums just get bigger and bigger, right? So the formula for the sum of an infinite geometric series doesn't really tell us anything about this. Imagine if we tried to use this. We try to use the s equals a sub 1 over 1 minus r, 1 minus r here. We would, in this case, we would have 3 halves over 1 minus, our r is also 3 halves. So that would give us -3. This doesn't make any sense, right? It's clearly not the sum when we add these things up. These partial sums are clearly not approaching -3, right? So in this case, this formula does not apply because our r is greater than 1, right? Or it also wouldn't apply if it was equal to 1. So our r has to be less than 1 for that geometric series formula to do anything for us, right? And if the sequence of partial sums doesn't have a limit, then we say that this series diverges. Every time we add on a new term, we get a larger and larger or smaller and smaller value, one that does not approach a specific value.